Since you like the, I see that you like the usable much, what is your preferred method of calibrating the NKT value?
One of the advantages of the CPTU is the ability to calibrate it against the undrained shear strength of clays. And that is essentially taking the tip resistance minus the total vertical stress and dividing it by a factor called NKT. The best way of matching that, I think, is a field vane shear. Because a field vane shear, I think, best represents the static peak strength in the simple shear mode. And then there is a relationship that NKT tends to decrease as the sensitivity of the soil goes up. And because you're measuring the tip resistance and the sleeve friction, you do get an indication of sensitivity with the cone. So doing a field vane shear test and then maybe 2 meters away doing the cone is a good way of calibrating that, and then you can use that cone with confidence in other locations. That's my preferred way.
There's another question towards the back.
Professor Gray was saying that one research that he made proved that only with 3 years or 1,000 days have a major improvement in the resistance of the soil due to aging. However, I have seen Andrew's work, and he's talking about 10,000 of years or 1,000 of years to get something similar in terms of improvement in soil resistance. So it's something regarding only the fields, or it's something that could be applicable to other type of soils?
No, I think you get an aging effect for clean sands, and it's a little bit more dramatic for silty sands and slightly plastic silts. And you see that in the laboratory for a certain period of time. Then I think you get to a point where you start to get some long-term aging effects. If there has not been an earthquake for a long time, then you do have an increase in resistance with aging. And looking at the shear wave velocity of the deposit and what the shear wave velocity of the deposit should have been is a good way of kind of looking at cementation and aging and taking advantage of those factors. There's some really good work that's been done by some investigators, primarily in the eastern part of the United States, where they have these older, sometimes Pleistocene, late Pleistocene deposits, where they know it would be overly conservative to treat them like young soils.
Okay.
Yes, just one more question. I would like to know which test do you prefer to find a critical strain line? You comment something related to triaxial compression test and simple shear, monotony and dry shear. So I would like to know your thoughts about that.
I most often use the triaxial compression test, an undrained loaded test to establish the steady state line. Michael Reamer, his entire thesis at Berkeley was using triaxial compression tests, triaxial extension tests, and simple shear testing to establish the simple shear line. The cyclic simple shear test would be the best because we normally are using things within the simple shear, often a 2D plane strain analysis, so that would be the best way of doing it. But I've sometimes found that it is more reliable to use a triaxial compression test, when you take the soil and consolidate to very, very high confining pressures, because you want to get to critical state, or as close to critical state, as soon as possible. So you want a test that gets there as soon as possible. You do have to lubricate your platins to to try to make sure you get more of a right cylinder deformation. So it depends. I've done it a couple different ways. It's not easy, but you're just trying to get close to it and use that framework.
You might have some answers on that too.
Yeah, we'll talk a little bit about that later on when we talk about residual strength of soils, but I would agree for kind of conventional tests, the triaxial test will get you closest to a steady state condition. But you don't, the deformation at those levels of strain are so large that you don't necessarily know what your strains are very well. But in a simple shear test, you have kind of arching and pinching in the corners of the sample that gives you quite a bit more non-uniformity. So I think the triaxial is the best. And I'll talk about a new experimental method, a new device that we developed to try to make those measurements more accurate and uniform. I think now, though, we should continue on with the scheduled program and talk about the simplified procedures that we use in practice for evaluating liquefaction potential. When we look at liquefaction problems and estimation of liquefaction hazards, there's really three questions that we need to ask ourselves. The first is whether the soil is susceptible to liquefaction. If it is the loading that we anticipate from our hazard analysis going to be strong enough to trigger liquefaction in the soil? And if it is, what are the effects going to be? And the effects are the most important part, but we usually get there to our evaluation of the effects by looking at these three questions. If the answer is no to the first question, we don't have to go any further. We may have other problems besides liquefaction, but we don't have to continue to evaluate liquefaction potential for soils that aren't susceptible. And if our loading is not sufficient to trigger liquefaction, either by virtue of it being a low, weak level of shaking, or we have relatively dense soils, then we don't have to consider the effects of liquefaction. But right now we're going to focus on the triggering of liquefaction, and later we'll talk about the effects of liquefaction. So the next 5 presentations will deal with the potential for triggering or initiation of liquefaction. And there's really 2 factors we need to consider: the loading that's going to be applied to the soil and the ability of the soil to resist that loading without liquefying. In our early days, these investigations were undertaken in the laboratory. And so Stephen and Lee, back in the mid-1960s, shortly after the 1964 Nevada and Alaska earthquakes, began performing cyclic loading tests, cyclic triaxial tests. And their loading histories were more closer to square waves than to sine waves. But even these early stages of testing gave us some good insights into the way liquefiable soils behave. And we can see that here, a measure of deformation, which is a measure of strain in these samples. The strain stayed quite small, even though the pore water pressure was slowly building up. And when the pore pressure reached a critical level, then all of a sudden the strains increased very, very quickly. As Professor Bray indicated, the results of laboratory testing were found to be very sensitive to the method of sample preparation, to the soil fabric, and because it was difficult to prepare samples in a lab that had consistent fabrics with those seen in the field, we shifted to a different approach. An approach that's based on field case histories of liquefaction and non-liquefaction that we currently use. And so our empirical approach makes use of documented case histories where we estimate the loading that is imposed on the soil during a particular earthquake at a particular site, and we measure the resistance of that soil. So we need a measure of loading and we need a measure of resistance. For a given case history, if liquefaction was observed, the loading and resistance was plotted and usually given by a solid symbol. If liquefaction was not observed, it was plotted with an open symbol. Cases that had high levels of loading, strong shaking, with loose soils that had low resistance would obviously liquefy, and they would plot in this upper left corner. Cases where we had weak shaking and dense soils would plot down in this lower right-hand corner. But there are a number of cases that were close to a boundary that could be drawn between cases where liquefaction was observed and liquefaction wasn't observed. And so this line that's drawn, this curve, marks the cyclic resistance of the soil, the liquefaction resistance of the soil. So we usually express the loading and the resistance in terms of cyclic shear stresses, and we refer to this as the cyclic stress approach. We use a cyclic stress ratio that I mentioned earlier to describe the loading, and a cyclic resistance ratio, which is the maximum cyclic stress ratio a soil can resist without liquefying, to measure the resistance. And we compare them by means of typically a factor of safety. We look at the ratio of the cyclic resistance ratio to the cyclic stress ratio, the resistance to the loading, capacity to the demand. It's the way we normally look at factors of safety in geotechnical engineering. We can also look at the probability of liquefaction occurring, which would be the probability that our resistance is less than the loading. So different ways are available to characterize the potential for liquefaction to occur. We have to make sure that we're treating the cyclic stress ratio and cyclic resistance ratio in a consistent manner, though. And so we'll talk about how we do that. In some cases, we may have soils that we judge to be susceptible to liquefaction, but we may be able to rule out liquefaction very quickly through a screening procedure. So this can save time and effort in eliminating the need to go through a detailed analysis. For example, we may have a site that is a very large distance away from the source of an earthquake. People have collected data on the greatest distance to which liquefaction has been observed in historical earthquakes. And they plot like this, and they show us that there are combinations of earthquake magnitude and distance where liquefaction has never been observed. And so if our site happens to be somewhere out here in this zone, we may be able to justify not performing a detailed liquefaction potential analysis because we expect the shaking is so weak at that large distance that there's no possibility for liquefaction to occur. Liquefaction has never occurred under those conditions before. If our soil is very dense, it may be too dense for liquefaction to occur. And so we may use different parameters that indicate the density of the soil and say that if our density, say if our standard penetration resistance is greater than 35 blows per foot, or QC1 NCS is greater than 220, or we have a very high shear wave velocity, that the soil is simply too dense to be liquefied. We can use our knowledge of the shear strain, particularly the volumetric threshold shear strain. If our soil profile is stiff enough, or the shaking is weak enough that the strains never exceed this volumetric threshold strain, that is, they never exceed about 0.01%, we don't expect any pore pressure to be generated. And if that's the case, we're not going to have liquefaction. We can use saturation, or the lack of saturation, as a screen. Pore pressures build up because the soil is saturated, and the pore fluid, then, the water that completely fills the voids of the soil, has a very low compressibility. Water has a high bulk modulus. If there's some air trapped in the soil, even a small amount of air bubbles, the tendency for the soil to want to contract is simply going to compress those air bubbles because they're very soft. The bulk modulus of air is very, very low. And so if you have partially saturated soils, you're very unlikely to build up significant pore pressures. And people are using desaturation or investigating at least as a potential way of mitigating liquefaction hazards. You can generate gas within the pore water in a liquefiable soil and maintain that gas so that it doesn't disappear or go back into solution in the water, you can reduce liquefaction potential. Drainage can be a factor that affects the buildup of pore water pressure. If you have only a thin layer of liquefiable soil and it's bounded by highly permeable soils, we may never be able to build up high pore pressures because high pore pressures may drain and be dissipated even during earthquake shaking. So this is another possibility that can allow us to avoid doing a full liquefaction potential evaluation. But if we don't have those conditions and we have a soil that's susceptible to liquefaction, we'll have to go through and do this evaluation. I'm going to describe a basic framework for doing that has a number of components to it, but the framework is consistent regardless of whether we're basing our soil characterization on cone penetration test resistance or standard penetration resistance or shoal velocity or any of the other techniques that we can use. So we're going to start with a computed cyclic stress ratio. And there's different ways that we can get that. Our cyclic stress ratio, remember, is the ratio of the shear stress, the cyclic shear stress, to the initial vertical effective stress. And so we can obtain this by various means. If we look at our laboratory tests, we typically perform laboratory tests using constant amplitude harmonic loading. We apply a sinusoidal loading to the sample. But in the field, the soil is going to be subjected to a transient shear stress history. It's indicated here. If these have the same shear stress amplitude, peak shear stress, you have many cycles being applied in the laboratory, but only one time do we reach that maximum shear stress in a field environment. And so these loading histories are not equivalent to each other. In some cases, we'll have a time history with one sharp spike that applies at high shear stress, and all of the other cycles are lower. And so we have had the concept of an effective cyclic shear stress that we take typically as a fraction of the maximum cyclic shear stress. And when this was done, the fraction that was chosen was 65%. It didn't have to be 65%, it could have been a different fraction, but if it had been a different fraction, other factors in this process would have changed to compensate for it. So in a sense, it doesn't really matter that we chose 65%, but we have retained the use of 65%. So we'll consider our cyclic shear stress in the field to be 65% of the peak shear stress. So then our cyclic stress ratio we can represent as 0.65 times the peak shear stress divided by the initial vertical effective stress. So this peak shear stress we can obtain in different ways. An easy way to do it, at least easy these days, is to perform a site response analysis and calculate for soil profile and the number of input motions the peak shear stress. We can plot peak acceleration versus depth. We did that yesterday using the program that I demonstrated, and we can just as easily click another button now and get the maximum shear stress and the profile of maximum shear stress. And you can see that it increases with depth, but it doesn't increase linearly with depth. It kind of curves downward as we go to greater and greater depths. And we can do these things now with Windows-based programs that have nice user interfaces, but when liquefaction analysis procedures were first being developed in the late 60s and early 1970s, it was difficult to do a site response analysis. You had to punch your data in on cards and take it to a computer center and give the deck of cards to an operator of the computer, and they would run the program overnight, and you would come back the next morning, and they would give you your output on big sheets of folded paper, and you would hope that there was no mistake, because if there was, you'd have to repeat the process. And it was very time-consuming. The data you would get would be a bunch of numbers on a sheet of paper, and you'd go back and get some graph paper in your office, and you'd start plotting things. So it was very, very difficult. And, so it was desired to come up with a simplified procedure that would eliminate the users from having to perform those kinds of analyses. And so we use this simplified procedure quite commonly even now. If we look at a block of soil that extends down to some depth in the soil profile, say at depth H, and we assume that it's perfectly rigid, then the inertial force acting on it is just its mass times its acceleration, and the maximum force would be its mass multiplied by the maximum acceleration. And so if it was rigid, that mass is going to be the volume multiplied by the unit weight, and the peak value then we could express as peak acceleration divided by gravity and multiplied by the total vertical stress at the base of that element, which would be this gamma h. If we look at the shear stress, though, in a site response analysis, we see, like we saw in the previous graph, that they tend to curve downward because the actual soil is not rigid, it's compliant. And if we look at the average behavior of many, many analyses, we can take the ratio of this maximum shear stress for a compliant soil and divide it by the maximum shear stress assuming a rigid soil and define a depth reduction factor, R sub D. And so we can then apply that to our rigid shear stress and write an expression this way. We have now still 0.65 tons of peak acceleration divided by gravity, so the value in G's, multiplied by the ratio of the total vertical stress to the effective vertical stress, and multiplied by this depth reduction factor. Depth reduction factor has been analyzed by different people who have prepared liquefaction potential evaluation procedures. Friedrichs and Boulanger developed a series of curves that look like this. For their procedure, the R sub D factor is a function of depth and earthquake magnitude. This is really a wave propagation issue, and we should expect that when we have a high frequency wave or waves traveling through a soft material, we'll have short wavelengths. And if we have a lower frequency wave or stiffer materials, we should have a longer wavelength. And for a longer wavelength, we should expect to see this depth reduction factor, in case anybody's wondering what time it is, in California, Washington, we would expect to have a longer wavelength. Well, we have longer wavelengths and larger magnitude earthquakes, but this doesn't account for the stiffness of the materials in any way. Chetton and Seed, in developing a different procedure, did a lot more analyses and a lot more soil profiles, and they chose soil profiles that were more representative of those in which liquefaction has been observed, and they developed a different relationship for R sub D. It includes the shear wave velocity of the materials in the upper 12 meters of the soil profile. And so by considering that, they can distinguish between shorter wavelengths and longer wavelengths. And so it makes a lot more sense from a dynamic standpoint and a wave propagation standpoint. Now, this R sub D relationship that Chetton and Seed have developed is part of their liquefaction triggering procedure. The one that that Idris and Boulanger developed is part of their triggering procedure. These procedures all the parameters of these procedures are developed together. So you can't take one component or one parameter from one relationship and use it in the other. So even though I like Chetton and Seed's R sub D factor better than Idris and Boulanger's, I can't take that and use it in Idris and Boulanger's procedure because it doesn't fit. They weren't developed together. So that's an important thing to keep in mind when using all of these types of components in liquefaction hazard evaluation procedures. These regressive relationships, since they're based on a large database, correspond to best to kind of average site conditions, which may be different than the conditions you have at a specific site. And so that's a factor that we want to take into account as well. If you perform a site response analysis on your specific site, you can account for as Professor Bray would say, the personality of your site, the individual characteristics of your site. And with the Chetton and Seed procedure, you're allowed to do that. With Idris and Boulanger's, they used their R sub D relationships to interpret their case histories. And so there's some effect of that in their liquefaction procedure, which means you have to use the same process in your evaluation in order to use their procedure more accurately and without introducing bias. Now, we know that the level of of pore pressure generation from the laboratory data that we've looked at already depends on the amplitude of the shaking, but it also depends on the number of cycles of loading that we're applying. And the number of cycles is influenced by the duration of the ground motion, and the duration of the ground motion is influenced by the magnitude of the earthquake. And so we have to account, if we're going to accurately characterize the loading that's applied to the soil by the earthquake, we have to characterize the duration in some way, and we do that by means of correlating it to the magnitude. So the number of cycles we assume to be related to the magnitude of the earthquake, and we use a magnitude scaling factor to account for that. And the magnitude scaling factor typically is plotted in a manner that looks like this. It's keyed to a value of 1.0 at a magnitude of 7.5. That's just become a standard, and we still use that today. So that magnitude scaling factor shows up in the denominator of the cyclic stress ratio. So for a large magnitude earthquake, say a magnitude 8.5, this would produce a magnitude scaling factor of about 0.8 or so. And that value of 0.8 going into the denominator is going to increase the cyclic stress ratio. If we have a small magnitude earthquake, say a magnitude 6, our magnitude scaling factor is about 1.5. And so if we put that in the denominator, it reduces the cyclic stress ratio. I think it was too heavy right now from the nice lunch I had. So we have a magnitude corrected cyclic stress ratio now. So this is the way we characterize our cyclic stress ratio in this simplified method. Now, sometimes you'll see it expressed differently. Some people prefer to consider the magnitude scaling factor in the cyclic resistance ratio and consider it as a resistance term. If you do that, then it's in the numerator of the cyclic resistance ratio. Since we end up taking a factor of safety as the ratio of the cyclic resistance ratio to the cyclic stress ratio, it doesn't really matter whether, numerically, it doesn't matter where you put it. I like to view this, though, as a measure of the loading that's applied to the soil, because we know that the loading in a long duration ground motion is more severe than the loading in a short duration ground motion. The magnitude scaling factor in newer procedures, such as Idrisen-Boulangers, is shown now to be influenced by the density of the soil, because the curvature and slope of the laboratory data that we see is influenced by, when we look at the cyclic strength curves, the cyclic stress ratio versus the number of cycles to liquefaction, those curves have different slopes for different soils of different densities. So their position varies, but their slope also varies, which indicates that there's a component of the resistance to liquefaction that's influenced by the density of the soil. And so that number of cycles relationship is influenced by the density of the soil. And so it has to be material dependent as well. This makes things a little more complicated in terms of separating out loading and resistance, but there are ways to get around that, at least to some degree. Then we have, when we've done that, we've computed a site-specific cyclic stress ratio for the magnitude of our earthquake, our anticipated earthquake, that's going to represent our loading. Then we're going to come over to the resistance side of the equation. And we will typically characterize the resistance by correlating it to some in-situ testing parameter. And there are more than one that can be used. Historically, we've used standard penetration test resistance, blow counts, and now we've shifted towards using CPT resistance. And the CPT offers a lot of advantages compared to the standard penetration test, and it's becoming a standard for evaluation of liquefaction potential. Both of those, though, require some adjustments for initial effective stress in the soil and for the fines content, because they are both influenced by those quantities. So if we look at standard penetration resistance, for example, there are a whole series of corrections that we have to make to our measured standard penetration resistance. So if N sub M is our measured penetration resistance, we need an overburden correction factor, C sub n, and some of the older ones look like this. We'll talk later about the newer ones. We need to correct for the length of the rods that are used. We need a correction for whether or not we have a sample liner. We need a correction for the diameter of the borehole, if that varies from the standard. And we need, of course, the energy correction. And we correct to a standard energy of 60% of the free fall energy, the theoretical energy in the standard penetration test. We should, as Professor Bray indicated, try to perform our tests in such a way that the energy that's actually delivered is as close to 60% as possible to minimize the amount of correction that we have to do. There's also a fines content correction. For many years, people thought that fines increased the liquefaction resistance of the soil because when you look at the graphs, the curves for higher fines content plot them above. But we now know that its effect really is to reduce the penetration resistance for either SPT or CPT. And so the way we handle that is to typically add a fines correction to the otherwise corrected flow counts. And so that fines correction for cone penetration testing looks like this. It's a function of the fines content. It simply tells us that we have a reduction in our penetration resistance when we have these fines. There's a similar correction that's made for standard penetration resistance. We're simply adding an increment of penetration resistance to the resistance that we've actually measured. So then we have a standardized in situ test parameter now. It would be a clean sand normalized cone penetration resistance or a clean sand normalized corrected standard penetration resistance. And there are relationships for liquefaction resistance, or the cyclic resistance ratio, that can be expressed as a function of those variables, the standardized in situ parameter, corrected to a overburden pressure of 1 atmosphere and to a clean sand condition, defines a fines content of 0. So we can then take our value and calculate a standardized cyclic resistance ratio. And that's going to correspond to a magnitude of 7.5, a vertical effective stress of 1 atmosphere, and no static shear stress. Those conditions may not exist at our site though, so we're going to have to adjust the standardized cyclic resistance ratio in order to match our site conditions. So we'll make an adjustment for the initial effective stress and the initial shear stress. For the initial effective stress, we're going to use a parameter K sigma, an adjustment factor, that's going to account for the fact that soils become more contractive for a given density as the effective stress level increases. This directly comes and is consistent with the concept of a state parameter. And so our K sigma value is going to be influenced by the vertical effective stress. It'll have a value of 1.0 at 1 atmosphere, and it'll decrease as the effective stress level increases, but the rate at which it decreases is going to depend on the density of the soil, whether we express it in terms of standard penetration resistances or cone penetration resistances. But we know these things, and we can calculate the value of K sigma. So again, it reflects the fact that the soil becomes more contracted at a given density with increasing effective stress. So it's going to cause our cyclic resistance ratio to decrease as we go to greater and greater effective stress levels. Professor Bray mentioned earlier, we asked the question, why would we use laboratory tests? Well, it turns out, as we'll discuss later, most of our data for field data for our case histories is from liquefaction that occurs in about the upper 8 meters or so of the soil profile. It's really quite shallow, but there are lots of instances where we're concerned about liquefaction at much greater depths than that. If we're dealing with a dam, where there's a retaining dam or a tailings dam, they're often very tall, and we have much higher effective stresses. Well, we can have liquefaction occurring at very large depths that never produces any evidence of liquefaction in the form of sand boils or ground movements up at the surface. Doesn't mean that it's not occurring or can't occur. Laboratory testing can allow us to go beyond the range of our empirical data and explore under controlled conditions the way in which pore pressures are going to be generated under these different conditions. For example, at very high effective stress levels. And so it's laboratory data that allows us to establish the position of these K sigma curves. It allows us to have a firm basis for extrapolating our case history data from 8 meters down to much greater depths. K alpha is a term that accounts for the initial shear stress. So if we have sloping ground conditions, we'll look at this K alpha parameter. And what we find is, as I said earlier this morning, that the behavior is complicated. If we have a very loose soil, say relative densities of 35% or so, shown in the lower band here, having a higher initial static shear stress reduces liquefaction resistance. But if we're at a medium dense to dense level, having initial shear stress will increase the liquefaction resistance. So this is a more difficult term to work with, and in some cases, people just assume K alpha is equal to 1. But it's a factor that needs to be taken into account and carefully perform liquefaction potential evaluation. So we can go either way with these shear stresses. Once we've done that, we will have a site and layer specific cyclic resistance ratio that will correspond to one magnitude, our effective stress level, and our initial static shear stress. And we can then compare that with the cyclic stress ratio that we've computed in the form of, say, a factor of safety. It's just going to be the ratio of the cyclic resistance ratio to the cyclic stress ratio. We're going to do this at every depth in our soil profile. So this will give us our final indication of liquefaction potential. So to summarize, there are a number of procedures that can be used for evaluating liquefaction potential. They are based on different in situ test methods. They're developed by different sets of investigators using different databases and different interpretations of case histories. So they're naturally not all going to agree perfectly with each other, but they have a number of options. Case histories are different. Quantities they use to describe the loading and resistance are different. The most commonly used procedures are cyclic shear stresses, but there are also shear strain-based procedures and energy-based procedures that we'll touch on briefly. Cyclic stress-based procedures, though, really dominate the field of liquefaction potential evaluation. The models have similar components. Multiple models have magnitude scaling factors, they have depth reduction factors, K sigma terms, K alpha terms. They're all interrelated within a given model because they're all developed together to be consistent with the data as interpreted by the developers. You can't mix and match. You can't take K sigma from one procedure and say, well, I like the magnitude scaling factor from this one and I like R sub D from that one, and put them all together. Your answer won't be accurate. It won't make any sense. So you have to be careful not to do that. Liquefaction evaluation procedures, as I said, are based on their case histories, and the case histories don't cover the entire range of conditions that we're interested in or need to evaluate liquefaction potential for in practice. In particular, very high densities, very high fines contents, large depths. Those go beyond the case history data that we have, and that requires us to extrapolate into conditions where we don't have that data. So we need to be very careful about how we do that, and the basis that we have, whether it's theory, steady state theory, whether it's experimental data from the laboratory, we have to use that information wisely in order to guide our extrapolations. So we should be using principles of soil mechanics as we understand them and available laboratory data when empirical data is not available. Okay, thank you.
Time for a difficult question for Professor Kramer.
Or an easy one.
Good afternoon. Could you please give us a key to choose the parameter M?
Excuse me.
Could you give us a key to choose the parameter M?
The magnitude?
Yes.
Okay. Well, the magnitude in a deterministic hazard analysis, if you use a deterministic analysis to estimate your hazard, your ground motion hazard, it's easy because you choose a particular magnitude, right? And when these procedures were being developed initially, that was the standard for hazard analysis. You would assume some earthquake scenario, some magnitude and some distance, so it was very clear which magnitude you should use. When your hazards and ground motions are developed by probabilistic seismic hazard analysis, there are a lot of magnitudes that are contributing to the hazard. And so what we most commonly do is to use the mean magnitude from the de-aggregation. So we can look at that de-aggregation, but we're plotting the contributions as a function of magnitude and distance. And you can sum over all the distances to get the contributions of each magnitude. That gives you essentially a histogram of the magnitudes that correspond to the hazard level that you have. It's most common to use the mean magnitude in the magnitude scaling factor of correction. What you can do is to use all of them and weight your answer by the probability of each of those magnitudes. That would be a better way of doing it. And we've written a computer program for our State Department of Transportation that gives them an option to do that, so they can consider all of the magnitudes. You can also go a step further and a step beyond what we're covering in this short course and do what's often referred to as a probabilistic liquefaction hazard analysis, or sometimes a performance-based liquefaction analysis, where you're considering all magnitudes and all levels of shaking and integrating over the entire hazard curve, rather than basing your liquefaction evaluation on only one return period. So there are more advanced and accurate procedures to do it, but for standard practice, the mean magnitude is most commonly used.